Thank you very much. And thank you for the invitation and the opportunity to present results of a joint project with Mariusz Lemańczyk, present here, and Sebastian Zuniga-Alterman on dynamics of B-free systems in Behrend case. I would like to stress out that the whole project is dedicated to the memory of Andrzej Szyncel, Polish mathematician who passed away recently. The setup is the following. We take a set of natural numbers without one, usually infinite. We always assume that it is primitive in the sense that elements of B do not divide each other. And this is not a restrictive assumption because we are interested in the set of multiples of B, that is the union of the ideals generated by elements of B, as well as we are interested in the complement of the set of multiples, so the set of B-free numbers, denoted by FB. Eta or eta B will always stand for the characteristic sequence or characteristic function, just indicator of the set of B-free numbers. This is a 0-1 sequence. The set of all 0-1 sequences is equipped with the natural shift by 1. And x eta will always denote the closure of the orbit of eta under the action of S. The closure is considered in the space of all sequences equipped with the product topology induced from discrete topologies from the sets 0-1. And this is just the B-free system or B-free subshift, I will usually say. This is x eta equipped with the automorphism S. This is one of the main objects of our study. It's worth to remember that a sequence X belongs to x eta if and only if every finite block that appears in X appears also somewhere in eta. This can be an alternative definition of the set X eta. Together with the B-free subshift, we consider something we call B-admissible subshift. To define it, let me say that a set A of integers is said to be B-admissible, provided it misses at least one residue class modulo every B belonging to B. By XB, we denote the set of all B-admissible sequences, that is, sequences whose supports are B-admissible in the previous sense. And these are, again, 0-1 sequences as before. And B-admissible subshift is XB equipped with the same shift automorphism. Of course, being admissible is S in pi. This is B. It's trivial that the set of B-free numbers is B-admissible because 0 residue class is always missed in B-free numbers. So the consequence is that x eta is a subset of xb. But usually, in general, they are not equal. The situation when they are equal is relatively simple. I will speak about later, but roughly speaking, this is not equality in general. Let me show you some fun example. Take for B the set consisting of the number 4 and all primes. This P stands for the set of primes. All primes which are congruent to -1 modulo 4. The indicator of B-free numbers looks like this. I don't know if it is instructive or not. This is the 0 position, doesn't matter. But it is an elementary fact, elementary observation that, of course, all numbers divisible by 4 are multiples of B, but also all positive numbers which are congruent to -1 and all negative numbers which are congruent to 1 are also multiples of B. And this observation yields that this is block consisting of 89 entries. This block does not appear in X eta. This block does not appear in eta in any place because it is, thanks to this inclusion, the only position in which you can meet something like 1, 1, 0, 1, 1 is this central position, the only place. However, this block is B-admissible. So this is a simple example of a set which for which the B-admissible and B-free subshifts are different. Let me also make the following easy observation, that whenever you have any set not containing 1, then if something is P-admissible, I mean admissible with respect to the set of primes, then it is B-admissible. So P-admissible subshift is always contained in B-admissible. This is easy observation. Another important thing is that the B-admissible subshift is always uncountable and it has no isolated points. With respect to uncountability, let me observe that it is enough to observe that there exists an infinite P-admissible set. And there are several constructions. Let me propose just a set of, I think it's called primorials of all primes. This set is infinite and it is easy to observe that it is P-admissible. So it is B-admissible for every B. Let me discuss another prominent example, the square-free subshift. This is the subshift defined by the set B consisting of the squares of primes. So our eta is the indicator of square-free numbers. This has been considered by Peter Sarnak in connection with Mobius function. And in particular, he proved that in this case, in the case of square-free subshift, the B-free subshift coincides with the B-admissible one. And also he calculated the entropy, topological entropy of the system. Let me present some strategy of proving that X eta equals XB, which can be applied also to this example and in slightly more general situation. You need some assumptions. First assumption you need is that B is infinite in coprime. Saying coprime, I mean pairwise coprime, that each elements are coprime. This assumption allows you to make the following construction. You take a finite B-admissible block. And having this, you can find a finite subset A of B such that this B appears in the indicator of A-free numbers. Not B-free numbers, but A-free numbers. This is I would say, an exercise of applying Chinese remainder theorem. Say B appears at this eta A over the interval from n to n plus small n, somewhere. It's easier to be A-free than B-free because B is bigger. It means that this eta A dominates eta B coordinate-wise. If we knew that the numbers in this interval are B minus A free, we would know that our block will be not, say, destroyed by the other elements of B, by the elements which are not contained in A. And in this case, B will also appear in eta B as we want. So we need something which assures that you can find this interval in a way that the elements of the interval are B minus A free. The assumption which helps is the following, that the sum of the inverses of elements of B is finite. And it turns out that it guarantees that this set of multiples of B minus A is, I would say, sparse enough that you can realize these constructions. I will come back to this in a moment, but before that, I would like to say some words about another property of B-admissible shifts, namely transitivity. Transitivity in topological sense, meaning that there exists a dense orbit. This means transit. One of our results is that for n set B, the admissible subshift is transitive if and only if B is coprime. Coprimeness of B is equivalent. Now I'm going into the idea of the proof. Coprimeness of B is equivalent to the following condition: that for every finite B admissible sets C and C prime, there exists a translation of C prime such that the union of C and C prime translated is still admissible. The implication from left to the right is easy. This Chinese remainder theorem, but the implication, the converse one, is more sophisticated. So you need to check.
It shouldn't be transitive or is equivalent to what you're saying.
This assertion is transitivity.
Yeah, but it's written coprimeness of B. It shouldn't be transitivity of.
Okay, this is true. Coprimeness is equivalent to this condition, and this condition is transitivity.
Ah, okay.
Okay, you're right,
okay.
And I'm also right. What I wanted to say is that this condition is just equivalent to transitivity, and it is relatively easy to see that when you can, if you have this property, you can collect all finite B-admissible blocks, and you can put somehow in one row inductively in one admissible infinite sequence, and this will be the generator of topological generator of the system. But as I told you, the implication from the right to the left is somewhat difficult combinatoric sense. But we have this. Let me remind that x eta, the B free shift, is always transitive by definition because it is a closure of the orbit of eta. So the equality x eta equals xb is possible only in the case when B is coprime. This is not this is a necessary condition. Coprimeness is necessary for this equality. Having this, we are always in the position to give some dynamical characterization of Erdős sets, and we call B Erdős, or we say that B satisfies the Erdős condition if it is infinite, coprime, and the sum of the inverses is finite. This is the definition of Erdős set. We have seen these conditions before when I was speaking about the proof of equality x eta xb. And what we can prove, actually, we have given almost all arguments, is that B is Erdős if and only if the B free subshift is equal to the B admissible subshift and the topological entropy is positive. I think about topological entropy in the terms of the complexity. Let me define the notion. The complexity of this B-free shift is the function associating to a number n, the number of blocks of length n that appear somewhere in this eta or x eta. And then topological entropy can be defined as the limit of logarithm of complexity divided by n. Now I'm going to discuss another property of the dynamical system associated with B, namely proximality. And you see, we are interested in finding some arithmetical conditions which correspond to dynamical properties of the system. I will present another result of this kind. A proximality of a dynamical system xt, say X is a metric space, means that for any 2 points in X, you find in the orbits of those points, you find as close as you want elements along some subsequence definitions written down here. In the B-free setting, x eta, it means that when you apply the condition to a sequence X and to its shift by 1, the condition means that X has to contain constant blocks of arbitrary length, arbitrary long length. But those constant blocks cannot be ones because we are in the B-free settings. So this means that proximality in this context means that eta has constant 0 blocks of arbitrary length. And it can be translated easily, or relatively easy, to arithmetical language. There is a result that proximality of the system is equivalent to the fact that B contains an infinite coprime set. Does not have to be coprime as a whole set, but contains something which is infinite and coprime. This is one of the results of a paper in which we collected several properties of B-free systems and B-admissible systems. This is one of them. Another important property of sets B, important in this context, is tauthness. The set B is said to be taut if every element of B is, I would say, relevant with respect to the logarithmic density of the set of multiples. When you remove any element from B, then the density, logarithmic density of the set of multiples decreases. Every element is important from this point of view. Logarithmic density is defined, logarithmic density of a set A is defined as this, and I would like to say that it always exists for sets of multiples. It's a theorem. And again, there is arithmetical, in a sense, condition equivalent to tauthness, namely, B does not contain any set of the form C times A, where C is a natural number and A is a Behrend set. And Behrend set, finally, is a set such that the asymptotic density exists and it is 0. Asymptotic density of A-free numbers. So most of the numbers are multiples of A, most in the sense of asymptotic density. In other words, toughness is equivalent to the fact that B does not contain a scaled copy of a Behrend set. Toughness is an important assumption in several theorems. In particular, I would like to show you a theorem due to Gerhard Keller, who proved that if B is taut and B contains an infinite co-prime set, which is equivalent to proximality, then this x eta is hereditary. That means that whenever you have a sequence belonging to x eta and a sequence which is coordinate-wise less or equal to x, then y is again is still in x eta. If B is taut and co-prime, then it turns out that B is L-dash. It is relatively easy to observe. And then x eta equals xb, as we seen before. And that is corresponds to this theorem in the following way, that xb is always hereditary. So in this co-prime case, everything is even simple. Thanks to this kind of results, we say that dynamics in the taut case is relatively well understood. This is because when you can compare x eta with xb, or at least you have heredity, you can, for instance, calculate entropy. You know more about this x eta. This is a relatively good situation. Since taut is something which does not contain a scaled copy of a Behrend set, so the natural step is to understand what happens when you take just Behrend set B. What is the dynamics in the case of a Behrend set? Let me give some simple examples of Behrend sets. The simplest, I think, is the set of primes. The only two P3 numbers are plus and minus 1, so the density of P3 is, of course, 0, so P is Behrend. But maybe this is not the most instructive examples. For B, we can take any set of primes such that the such product is 0. And such set B will be Behrend. And this is because in co-prime case, this formula gives you the density of B3. For instance, you can take all primes in arithmetic progression, provided this progression contains at least one. By Dirichlet theorem, in this case, you are in this situation and you arrive with a Behrend set. The first example I showed you was a Behrend set. There's a simple proposition which produces Behrend sets. If you have two Behrend sets, then this kind of product is again Behrend. So, for instance, semi-prime numbers, by this I mean numbers which have exactly two prime factors, form also a Behrend set. Similarly, analogously as in the L-dash case, we have a nice dynamical characterization of Behrend sets. It goes as follows. B is Behrend if and only if the B3 subshift is proximal and the topological entropy is 0. Proximal with topological entropy 0 are just Behrend sets. The implication from the left to right is, okay, if you assume Behrend, proximality follows by elementary arguments. Topological entropy can the zero can be calculated, I think, by some classical inequalities. This is, I think, something classical, I would say. But the converse implication is more sophisticated, and to prove it, you need to collect several observations, several results from the papers Keller, Lemańczyk, Ricard, and Sell. And I think that the crucial observation is made in the paper by Joanna Kułaga and Michał Lemańczyk. But I will not go into details of this proof. I just want to stress out that there is such a nice dynamical characterization. The corollary from this is that the complexity of a Behrend system is always sub-exponential because topological entropy is zero. And next result I want to show you says that in a sense any sub-exponential complexity can be achieved by a suitably chosen Behrend set B. So more precisely, we have the following theorem. When you have any function which behaves like that, rho n by n tends to 0, then you can find a Behrend set consisting of primes such that, in a sense, the complexity of this eta, of this B-free shift, is at least 2 to the power rho n, in a sense. And moreover, which is not typical for Behrend sets, the B-free subshift coincides with the B-admissible. The proof is just a construction of the set B. You can imagine that you inductively construct finite subsets, increasing family of subsets, and B will be the union. And I believe that for people working in dynamical systems, this construction is something standard. Let me show you the idea of the passage from the K stage to the K+1 stage. Imagine that this bar represents the set Bk, or the interval in which Bk is contained. Bk is already constructed. And as an inductive hypothesis, you have to assume several things. In particular, this is done in this way, that every Bk admissible block of length k appears somewhere in this region in eta Bk. Then you leave some free space. You choose n large enough that this inequality is satisfied. Density of Fbk is positive because Bk is finite, so we can reach it. And empty means that you will not take any elements from this interval to your set B. And also, this interval is long enough that every Bk admissible block of length k+1 appears in eta B somewhere in this region. So something has to be assumed before about Bk, but okay, this is stable. Then you take several consecutive primes so that this product is small enough in the sense which has to be made precise. And then you leave some free space, and then you take consecutive primes, and then you leave long free space, and so on, so on, so on. And the idea is that the union of the sets Bk constructed in this way is Behrend, this is Behrend thanks to this small enough choices of these products. Every admissible, B-admissible block appears in eta because it appears in one of the gaps we left free. And finally, the complexity is achieved because in eta, in these regions, you find length n blocks with the frequency of ones, which is at least like that, at least this. And this means that in eta you meet at least row n ones in this region, and comparing it with other properties, you arrive with this statement of complexity. This is technical, but the idea is more or less, I hope. Let me go now to something we call the subshift of primes. So first of all, let me put this formula in our notation. What does it mean? P2 is the set of semi-primes. So semi-prime free numbers are the numbers which has at most one prime factor. That is, they are primes, maybe 1 or -1 or minus primes. We shall use the following convention, that given a set A of natural numbers, we will denote by X indicator A, X indicator the union A and minus A. And the later is the subshift defined by the characteristic function of this union. That is the closure of the orbitals concept. Just to shorten the notation, you write this instead of this. Under this convention, we can write that this the subshift defined by the set of primes together with the number 1 is the same as the B free subshift, where B is P2 free subshift. Okay, so this follows by this form. Clearly, as for any set B, this is contained in P2 admissible subshift, but of course, for many reasons, this is not equal. One of the reasons is that P2 is not coprime. Equality can happen only in the coprime case. But this is one of the reasons for this. This subshift has isolated points. But when you remove isolated points, you will obtain something, you will obtain the same if you remove isolated points from the subshift induced by the set of primes, something more natural than this. And without isolated points, this difference is contained in the set of P-admissible elements. And this is because if a block appears infinitely many times at the indicator of P, then it must be P-admissible. It is not true that every block appearing there is P-admissible, but those that appear infinitely many times are P-admissible. But the converse inclusion is, I would say, out of reach now, because it depends on big conjectures like Hardy-Littlewood or Dixon's conjecture, which, if we would assume the conjectures or one of them is true, we would conclude that every P-admissible, that the P-admissible subshift is contained in the prime shift. in particular, conditionally on the conjectures, this what I call the prime shift, prime subshift, would be uncountable because this is always uncountable. But at the moment, I only formulated conditional. Andrzej Szyncer informed us once that this uncountability of this shift is a consequence of the conjectures. And this is one of the reasons, maybe not the main one, but one of the reasons we dedicate this project to his memory. I think everybody knows better than me what are the conjectures, but let me say some words. Each of the conjectures has a consequence that every finite p-admissible set is prime producing, in the sense that there are infinitely many numbers k, such that the set is h1 up to hr, k plus h1 and so on, k plus hr are all primes. But each of the conjectures has a slightly stronger consequence, that every p-admissible set is prime producing in a strict sense, I would say. That is, for infinitely many k, the numbers k plus h1, k plus hr are prime, but the numbers k plus h are composite for h taken from this interval from which we subtract the chosen set. So this strict sense depends on the interval in which we consider the set. A more precise formulation of the quantitative form of Hardy-Littlewood conjecture would be can be formulated as follows: that the frequency of, when you take a p-admissible set of integers, that the frequency of prime constellations which look like the set is something like x by log to the power kx. And I think that really conjectural is that this is the lower bound, and the upper bound is a theorem now. But I think we can formulate it in this way also. Dixon's conjecture can be expressed in terms of a family of linear polynomials with integral coefficients, and it asserts that when you have a finite family of such polynomials and you assume something like this, then this family is prime producing in the sense. And this something is a condition that is written for any p. There is an integer such that the product of f, I, y is not divisible by p. So the assertion is that if there is no obvious arithmetical reason, obstruction, then this family will produce primes for infinitely many. Okay. We are interested in the complexities of our systems. So what about the prime shift? There's a theorem, and we have an upper bound for the complexity of the prime shift, and the upper bound is like 4 to the power n by log n. The same upper bound is valid for the complexity of p-admissible shift, while the lower bound is something like a 2 to the power n by log n. And this is unconditional. But if we assume Hardy-Littlewood or Dixon's conjecture, then we have also lower bound for the complexity of the prime shift. And this is exactly the same expression. This was communicated by Tao, and the proof is due to him, and goes and it's based on prime number theorem with respect to the lower bound and the large sieve methods with respect to the upper bound. And let me give you some indication how to do it. The lower estimate for, say, for p-admissible shift goes as follows. First, observe that when you take primes in the interval n+1 to n, then this set is p-admissible for every n. And this is the number of primes in this interval is p2n minus pn, and this is something like n by log n. So the lower bound of the number of p-admissible blocks of length n is 2 to this power, because any subset of this is p-admissible. From this you arrive this lower bound. So this is valid for p-admissible blocks, but assuming, for instance, Hardy-Littlewood or Dixon's, this is also lower bound for the complexity of the prime shift. So that's about lower estimate. Upper estimate depends on the large sieve methods, and the crucial observation is that for a p-admissible set contained in some interval, as it is p-admissible, we can fix some sequence of residue classes, modulo primes, that are avoided by A, because it is admissible. It's enough to restrict our attention to primes less or equal to the square root of n. And large sieve gives us an upper bound for the cardinality of the rest of the interval. We remove those residue classes, and the upper bound can be something like 2n by log n. Further, let Bn stand for the number of the sequences of residue classes, modulo P. Sequences of residue classes, the choices. This number is clearly the product of the primes less than or equal to the square root of n, and this is something like exponent of the square root of n. So, combining the two things, the upper estimate for the number of p-admissible blocks of length n is 2 to the number Cn, this is what was previously discussed, times Bn. So this is 2 to the power 2n by log n times this. The first term dominates the second one, and it can be replaced by this, and we are done. This is upper bound for the complexity of p-admissible shift, and at the same time, the complexity of the prime shift, because the number of blocks appearing in the prime shift, which are not p-admissible, is small. They're on the initial blocks, so they have no influence on the complexity. We also looked what we can prove about the semi-prime shift defined analogously, and I will only show you the result. There is an upper bound for the complexity of the shift given by 4, again 4, but to 23n log square log n by log 4 times log n. So it differs than the previous one. Sorry, that's not a good idea. It differs from this basically by this term. Under Dixon conjecture, I don't know if heredity is enough here, but thanks to Dixon, assuming Dixon's conjecture, we can also provide a lower estimate for the complexity, and this is 2 to n log n by 2 log n. About the proof of the lower estimate, I would like to tell you that it is based on something which, in my opinion, is classical. Frequency of pk is okay. We are interested in p2, so k is 2 for us at the moment. So we have this, and assuming Dixon's conjecture, we can prove something which is, this is a combinatorial result, saying something that if you have a subset of semi-primes contained in some interval, and the interval satisfies something, then this set is, I would say, semi-prime producing in a sense. And having this, you just obtain this lower number. But I would like to finish the talk by telling you what can be done unconditionally, because it is the most important. So there is a recent paper by Tao and Ziegler, and its main result is the theorem on subsets of integers, but they also provide the following theorem. If you have an infinite p-admissible set of natural numbers, then you can find inside A an again infinite subset A prime, such that it appears as a support of some element of this prime subshift. And having this, you can conclude that the prime subshift is uncountable. While working on our project, we was not aware about this fact. We could argue that this is uncountability based on Dixon's conjecture or heredity. Now we know that this is true unconditional. Thank you very much for coming and for the attention.
Okay, so do we have questions?
Is there any reason, so for the complexity in the semi-prime case, do you expect either of the exponents to be correct? So which one? In your bound for the complexity in the semi-prime case?
Yes.
Your exponents are different, right?
Yes. You know, the reason. I would say that when you consider semi-primes or P3 or P4, this will be the situation, that the exponents will be different. So only in prime case, perhaps I would say by an accident, the exponents are basically the same. But I don't know if I'm right. Okay. They are different because we could elaborate only these exponents, but well, it seems to me that this is just a natural situation. But maybe it's possible to find better estimates. Of course, it's possible.
Okay. So if not, so let's thank Staszek again. Thank you.